Hello everyone, today we'll talk about the solution to the problem path with maximum probability. We're given a weighted graph we want to get from start to end, and we want to get there with maximum probability. And that probability comes from the fact that every edge has some assigned probability of success when it comes to traversing that edge. So let's say there are bridges, and there is unfortunately some probability that we fall from that bridge to our death. And of course we don't want to die, so we want to find a path such that the probability of us dying along the way is as small as possible. So probability of us traversing all the bridges, all the edges successfully is as high as possible. And of course, in this case, the probability of successfully traversing every bridge is independent of the others, which means that if we just select some path from start to end, the probability of us successfully going through it is just the product of probabilities of successfully going through every bridge on that path, every edge of on that path. So in other words, we want to find a path from start to end that has the biggest product of the values on the edges. The first thing that might come to mind when solving this problem is the similarities and differences between this and the classic shortest path problem that we can solve using Dijkstra's algorithm. Dijkstra allows us to find the path from start to end that has the smallest sum of values on the edges. But we don't want the smallest sum, we want the biggest product. So how different is it with the biggest product? Well, certainly the biggest should be quite scary. That's because while Dijkstra allows us to find the shortest path, it does not allow us to find the longest path. If you've never thought about it, then it's a good thing to think about it. To know that Dijkstra does not allow us to find the longest path from start to end. And it's useful when you want to try and use Dijkstra's algorithm to solve a different problem, to either know how to transform your problem to a problem that Dijkstra can solve. So the problem where we want to minimize the sum of values on the edges, but that can be quite difficult and not really that clear. Or to understand why Dijkstra's algorithm works, and in that case you can just see if the algorithm works, if the proof works in your case, and in that case Dijkstra's algorithm will also work. And the main idea when it comes to proving the correctness of Dijkstra's algorithm is that at any point, so when we have the algorithm that is running, we start with the start node, then we add some other node to it, then some other node to it, then some other node to it. We process nodes one by one. And at every point we have some cloud of already processed nodes. And now there are some edges that go from nodes in this cloud to some nodes outside of this cloud. Let's say A, B, C. And we want to select one of those nodes outside the cloud to add it into the cloud of already processed nodes, where we know the shortest path to get to that node. And the idea here is that from all these nodes, we can take the one that has the smallest cost of getting to it, and we know that this is indeed the shortest path from the beginning to that node. For that not to be the case, it would be that we can go to some other node that has a cost that's not smaller, so at least as big, and then there can be some magical path over here that gets back to this node that had a smaller cost at the beginning, but the total cost of going to B and through that weird path is smaller than just going straight up to A. And that can be true if, for instance, that path has weight that's negative. So, for instance, let's assume at the beginning that we can get here with cost 1, here with cost 2. Then, while A seems to be the best, in fact going to B, paying 2, and then going through this minus 2 path is better than paying 1 and going to A. So in that case, Dijkstra's algorithm doesn't work. But if all the edges have non-negative weights, then Dijkstra's algorithm works, because it's impossible to first go to a more expensive node, and then through some magic, go to a node that was at first cheaper and suddenly be even cheaper than that node was at the beginning. And it might be more clear in a specific example, because it works in this case. And the specific instantiation of this line of thinking is that if through all the nodes that we have already processed, we know that the best way of getting to some new node is with some probability, and all the other new nodes have at most that probability, so they are not more probable, then it's impossible to go to a node that's at most as probable, so let's say less probable than the node we're looking at, and then through some weird path, arrive at the node that at the start was more probable with an even bigger probability. It's clear that it's impossible. So for instance, if we have our cloud, and here is an A, here is a B, if we have a probability of survival 0.8 here, and probability 0.7 here, there is no way of going through that 0.7 and then somehow ending up with something bigger than 0.8 at A. Because that number can only stay the same or get smaller along the line. So that is enough for us to know that, okay, we can use Dijkstra straight up. And in that case, we want to first take our edges and weights of edges, transform them into a graph. So this is a standard adjacency list representation. We'll be maintaining the distance for every node, and also a priority queue. Since we want that priority queue to be give us the smallest value, then we have to, well, the easiest way is just to push negative values onto our priority queue. This is a standard trick that you can also use in C++. There are other ways of doing that, but this is one way to just maintain not the probability on priority queue, but the negative probability. But we always want to take the node that has the biggest probability of all the nodes that were not processed yet. And we start with the start node. So we look at that probability. This line here is not necessary, but it makes sure that we only process the node once. Every node is only processed once. And then for every neighbor of that node, we have an edge with some weight. So we can get the probability of getting to our current node, which we know from the priority queue, or from the res array, multiplied by the weight of that edge, and that is one way of getting to the neighbor. And if it's better than what we currently know about the neighbor, we update the highest probability of getting to the neighbor, and we push with that value onto the priority queue that neighbor. Of course, to use priority queue, we use heap queue, the heap queue module with heap pop and heap push. And at the end, of course, we have either not got to end, in which case it's still 0 and we return 0, or we just return the probability, so minus what is written in the res array. So knowing how to prove that Dijkstra's algorithm works can let us solve this problem, see that Dijkstra works in this problem. However, if we, for instance, only had a black box Dijkstra that only worked in minimizing the sum of weights, there is actually a way of converting the weights that we have into weights that we can just add up together. There are no negative weights, and we want the path that has the smallest sum of weights. And this is using the typical tool for transforming between multiplication and addition, which is logarithms. And in particular, the most important rule when it comes to logarithms is that logarithm of a product is the sum of logarithms, because everything stems from this thing. This can be used for multiplying numbers using lookup tables, which is an old-timey way of multiplying numbers. So you have two numbers, you want to multiply them, then you can look in a table for the logarithm of one number, logarithm of the other number, add them together, and then look in the table for the logarithm of that sum. So look for that sum in the table of logarithms, and it'll tell you, okay, that sum is the logarithm of this value, and so this value is the product. But this allows us to go from product to sum, or from sum to product, but in this case, and it's typically used for going from product to sum, and all the logarithms along the way are negative, so we can just take minus logarithms. And in that case, if we transform every edge weight into minus logarithm of that original edge weight, then our problem is just to find the smallest sum of weights of edges from start to end, which is exactly the classic shortest path problem that Dijkstra works out of the box with. So that is one other way of convincing yourself that it works. And if you're not that familiar with logarithms, then think about it and try to make sure that it actually works and why it works.